So to get a better understanding of why our emitter follower or common collector amplifier configuration is useful, let's take a look at the output resistance. So in order to determine this, we're going to use something called the test source method, and we're going to be applying this to our small signal equivalent circuit, which I've copied here from our previous video. So with our test source method, the first thing we want to do is to deactivate any independent sources. So deactivate our independent sources. So in this case, we only have one independent source, our VS, and because it's a voltage source, we deactivate it by replacing it with a short circuit. So we get something like that. And then in terms of our test method, what we're doing is we're coming over here to our output terminals, and we're going to be applying a test source. Now, whether this is a voltage source or a current source in terms of our calculations doesn't really matter, because regardless of which one it is, we're going to say it has some voltage Vx and some current Ix. Now, if we're actually doing this in the lab, of course, oftentimes it's going to be easier to use a voltage source. So then what we can say is our output resistance is going to be the resistance looking in to our output terminals. So that's going to be R naught, which by definition is going to be equal to Vx over Ix. And so a lot of times when people are using this test source method, you'll see that they set the test source to be a 1 amp current source. The reason is then you have 1 amp here, so really you're just solving for Vx. To be consistent with the notes, I'm going to keep it as a general Vx and Ix, however. So what we can do is we can start by doing a node voltage. So let's do a node voltage equation. And so essentially what we're doing then is basically just KCL, right? So we're looking sort of at this top node, and we're going to sum all of our currents. And so doing that, we can say we have a negative Ix coming in from that test source, and then we're going to have Vx across each of these three branches here. Of course, we're not really concerned about it on that dependent current source, but we have it across those two resistors. So we can say we have some current Vx over Re plus Vx over R naught. And then our dependent current source still has negative Gm V pi. And then finally, we need to deal with this mess of resistors over here on the far left side. And so what we can see is now that that Vs is deactivated, we have these two resistors in parallel, and then that combination is in series with our R pi. So sort of putting all of that together, we have Vx over that equivalent resistance, which again is going to be our R pi in series with the parallel combination of what we already had was R1 parallel R2, and now we're putting that in parallel with our RS as well. That is all of our currents, so we set that equal to 0. So we still need to relate our V pi to our Vx. So we still have this V pi term in here, which we want to get rid of. So we need an additional equation to relate that V pi to Vx. And so the way we can do that is by using voltage division over here on this side. And so I'm going to redraw the circuit so it's a little bit easier to see. So we have a Vx voltage here. We have our R pi resistor, which I'm going to go ahead and draw like this. And then we have this combination of RS, R1, and R2. So this is our Vx voltage. This is R1 parallel R2 parallel RS. And this is our R pi. And so notice our V pi is positive at this terminal and negative at this terminal. So we have something that looks like this. And so again, the reason I've just drawn this Vx directly connected to that is because we know Vx is between this terminal. And of course, if we sort of extend that over, we see that it's between these terminals that are the input to that voltage across that whole resistor network here. So that's why I've sort of drawn that equivalent circuit that way. So now, as I was saying, all we have to do is voltage division. So from voltage division, we see that our V pi is equal to negative because of the difference in the polarity orientation of R pi divided by R pi plus the other resistor, which is R1 parallel R2 parallel RS. And then we multiply that by that input voltage, which is Vx. So now if we take this V pi equation and we substitute it into this previous expression to get rid of V pi, so now we have everything in terms of Vx, Ix, and resistor values and parameters for our transistor. So what we can do is we can sort of solve that for, again, we want to find Vx over Ix because that's equal to R naught. So I'm not going to go through all of that algebra, but if we do that, what we end up getting is that our R naught is equal to R pi plus that parallel combination of R1, R2, and Rs. And then we also need to keep in mind that our R pi times Gm is equal to beta. So we had talked about that previously, so with that in mind, we then have a 1 plus beta down here, and that whole term in parentheses is going to be some resistance value, which we're going to say is in parallel with Re, which is in parallel with R naught. So that's going to be the expression for our output resistance. And again, keep in mind, this is for the particular circuit that this small signal equivalent came from. So if we adjust that configuration slightly, we need to reanalyze our small signal equivalent to get an updated R out. Okay, so as we often do, we can make some simplifying assumptions about this equation to get a better sort of general feel for what this R naught is. So typically our RS value is going to be small, because remember that's our internal source resistance. So typically RS is small, and in an ideal case, that's going to be 0. So ideally, RS is going to be 0. And so if it's 0, then that parallel combination is just going to be 0. But if we keep it more general, we can say R1, R2, Rs all in parallel. Because Rs is going to be really small, that parallel combination is approximately Rs. Because remember, a smaller resistor is going to dominate a parallel combination. If that doesn't make sense, you can play around with some numbers in the parallel combination equation and it should become pretty obvious. And so we're saying that this Rs is approximately 0 in an ideal case. So what that means is we can essentially ignore this term here. So now we have R pi over 1 plus beta in parallel with Re and R naught. And so remember, our Re and our R naught are typically going to be a few k ohms. So not even into tens of k ohms usually. Re sometimes will be even smaller than that. For example, in the circuit we saw, it was set as 2k. With our common emitter circuits, we saw it was hundreds of ohms. Our R naught typical values 3 to 5k we've seen before, I believe. So we compare that to our R pi, which again is also k ohms, but our R pi is being divided by 1 over beta, or sorry, 1 plus beta. So this value, again keeping in mind that beta is on the order of 100, is going to dominate that parallel combination because it's going to be much smaller. So this will dominate our parallel combination because again we're assuming that that beta is a relatively large number, much greater than 1. And so what that means then is that our overall output resistance, R naught, is relatively small. So relatively small, and it's actually approximately equal to that R pi over 1 plus beta. So we have k ohms divided by about 100. And so what this means then is that our common collector amplifier, or our emitter follower, is behaving like an ideal voltage source. And so what I mean by behaves like an ideal voltage source is that it's not sort of being loaded down as we're changing our load. So rather our output voltage isn't a strong function of our load resistance. So behaves like an ideal voltage source. And so on that we can say minimal loading when other circuits are connected to the output. And so for more details on loading, we had talked about that before, but you can go back to page 413 and review that as well. And so for this reason, because it has minimal loading when we connect other things to the output, oftentimes we're going to use this common collector emitter follower. So oftentimes we're going to use that as the output stage when we have a multi-stage amplifier. So oftentimes used as our output stage. in a multi-stage amplifier. And so we're going to come back and talk about multi-stage amplifiers really briefly in a few videos from here. But the basic idea is sort of the same as we've talked about generally before. If we have multiple blocks and we're cascading different amplifiers, we're saying that this common collector or this emitter follower is a good output stage because it has a low output resistance. Why is that important? Because it means our output voltage isn't going to be varying as we have different loads based on our loading effects arguments that we considered previously.